Welcome, welcome. This is 49E5 and we're talking about vector electric force equation. This is basically the same form as we had for Newton's universal gravitation equation. The force of attraction or repulsion between these two charges will depend upon the size of the bigger charge, let's call it big Q, and the size of the smaller charge, little q. And as they get bigger, the force will get bigger. That makes sense. So put those on top of the equation. And it's going to also be affected by the separation between the two charges. And as the separation increases, then I expect the force to decrease. If that's not the case, then a charge on Pluto will have as much effect on a charge on my desk as a charge on my desk will have on its neighbor. That can't be right. So it's got to fall off with distance. So put R on the bottom, and I can tell it's a squared relationship. It's an inverse squared relationship, because if you imagine the effect of a charge passes away, extends outwards over a sphere, and the area of the surface of a sphere is 4 pi r squared. If the influence is over a small sphere, and then the same influence is over a big sphere, if you like, the influence has been diluted or spread out or made less intense, and therefore I expect that its consequences will fall off with the inverse square, because the consequences are spreading out over a larger area. So it makes sense that this is an r squared, 1 over r squared relationship. We need a constant to make sure the numbers work out, dependent upon the units, and we have a thing called Coulomb's constant. And that's magnitude. So if I want to know the size of this force, I can plug in numbers and get the size of it. If I want to know the vector force, I need a direction with it, and so I apply a unit vector. And the unit vector points me in the right direction. It has a magnitude of 1. So it doesn't change the size of the force, it just indicates the direction. And if I have this unit vector, then I get a vector force rather than a scalar force. So, look at our diagram. What we see is, we have in this case, it looks like it's two positive or two negative charges. We have the same charges. How do I know that? Because the force is going away. And I have a vector that links one charge with the other. And I've invented a unit vector, which in this case is in the same direction as the displacement vector between the two charges. So when I write this equation, this is the diagram I'm thinking of. Ke is called a Coulomb constant. It's a big constant. It's 9 times 10 to the 9 Newton meter squared per Coulomb squared. Compare the size of this with Newton's, with the gravitational constant, which is tiny. So this is a big effect. And little q is measured in coulombs, or charges are measured in coulombs. R, the distance between the two charges, is in meters. Notice that r hat is not the same as r. If they were, you could cancel them, but they're not the same. One is a vector, it's a unit vector, and the other one is a number, it's a distance. So they're not the same animal. They just happen to have the same letter used in the equations. So r hat is a unit vector that points in the direction of the force, And then it's best to consult your diagram to get the unit vector direction correct. In the textbooks, often you'll see they put a sign in this equation and they have a subscript on the direction, and that works great. They're assuming a certain geometry for the setup, and if you understand that geometry, it works great. The danger is people don't remember the geometry, and so they just willy-nilly put a sign into the equation whether it needs it or not. I've gone to the other extreme where I say, I'm not going to put any signs in this. I need you to look at your diagram and work out which direction the force will act. So, then the next thing is a little word of warning here. So I remember working in a department once, and we were a physics department, so we would produce this as basically Coulomb's force law. And then we handed our students over to other departments, and as they graduated from us, and one of the other departments decided to do a quick test to see if the students were prepared when they came in. And to their sort of shock and horror, they found that their students didn't even recognize this equation, and they, in a way kindly, they contacted us and said, hey, what's going on here? And we were perplexed, and then we realized that in physics departments, you tend to say F is equal to KE big Q little q, or Q1 Q2, whichever you like, over R squared, where you use KE as the constant. Whereas in other departments, like I've seen it in some electrical engineering departments, they will say F is equal to 1 over 4 pi epsilon naught big Q little q over R squared. And my sense is what was probably happening was the students were seeing this, that somebody from a physics program would probably not have seen much of, and not recognizing what it was and saying, I don't know that equation. So be careful when you transfer from one department to another, one field to another especially. Even though you're doing the same science, you might have different traditions, so watch out for that. Let's do a few of these. Let's start off conceptually. So I have a diagram here. I have two charges in interstellar space, so there's nothing around, and one is charge R and one is charge L, and all I know is there's a 18 Newton attractive force between them. That's all I'm given. So think about it for a while, and then try and answer these questions, and if you like, stop the tape before you see the answer. So point charge L, which is on the right, which is kind of confusing. Point charge L is located some distance from point charge R. Charge L experiences a force of 18 newtons towards R. Do the two charges have the same or different signs of charge? So think about it for a minute. And the answer is that they must have different signs of charge, because it's an attractive force. If they were both positive, it would be a repulsive force. If they were both negative, it would be a repulsive force. The only time you get an attractive force is when they have opposite signs. What size of the force is experienced by charge R? Well, think about it. And the answer is that it's an action-reaction pair. Remember that? The force of charge 1 on charge 2 is equal and opposite to the force of charge 2 on charge 1, because they're an action-reaction pair. And so I know it's the same size, and I know it's going to be in the opposite direction. So the size will be 18 newtons. In what direction? Well, it's going to be towards L, because it's the opposite direction. And then what can you conclude about the magnitude of the two charges? Think about this one. I'll give you a second or two to think about it. Shut the tape off if need be. Really try and decide for yourself what you think. And I'll start now and say, and you can conclude, does it L equal R? Same force or nothing? And the answer is absolutely nothing. And at first that might catch you off guard, and it does most people. But remember, the force of me pulling on the earth is the same as the force of the earth pulling on me, because we're an action-reaction pair of forces. Now, the consequence of that force is much more significant with me because my mass is so small, my acceleration is quite noticeable. Whereas the consequence on the earth of me pushing away from it, although it's the same force, because the mass is much bigger, it's a much smaller, much less noticeable consequence. And so we tend not to pay attention to it. But you can't tell. They could be the same size. They could be any two sizes you want. You cannot tell. You can't say which is bigger. You can't say which is smaller. You can't say if they're the same. So don't be upset if you miss that. People do. But just, remind yourself of it. And then this last bit on this page is, what force would point at charge L experience if the separation between the two charges were tripled, the magnitude of R was doubled, and the magnitude of L was quadrupled? So I can say the magnitude is equal to KE big Q little q over R squared. And I'm talking about magnitudes here. So then the next thing I need to do is say, well, what happens if I change some of these things? The best way to do this, it's a problem of layout. So the new force over the old force is equal to the new force, which I don't know, over the old force. And I do know the old force was 18 newtons. And this equals, KE Q nu little q nu over R nu squared over KE Q old little q old over R old squared. So I can say, well, let's have a look. This is going to be KE, and it says here, if the separation between two charges were tripled. So I don't know what the separation was originally, but I know it's 3 times bigger now. So let's call our old separation 1 and square it. And let's call our new separation 3 and square it, because the separation between the two charges were tripled. And then the magnitude of R was doubled. So let's say, well, I don't know what it was, but I know it's twice as big now. So call that 2 and 1. And the magnitude of L was quadrupled. So I don't know what it was, but it's 4 times bigger now. So let's call that 1 and 4. And then I can start to cancel. And can you see the KE's go away? I get 8 over 9. And a lot of people who do all this work will then tell me that the new force is 8 over 9 newtons. And the chances are they're not writing all these steps down, because I look at this and I say, oh, Fn over 18 is equal to 8 over 9. So Fn is equal to 8 times 18 over 9, which equals 16 newtons. So these ratio problems, I think, are quite valuable. They're quite useful. And it's layout. If you try to do them in your head, chances are you'll make more mistakes. So try to get the layout right. And just go through and do the ratios. If it's a tenth, put down 1/10 over 1. If it changes to 1/4, put down 1/4 over 1. If it's 17 times bigger, put down 17 over 1. But just lay it out the way it should be, and you'll get them right pretty well every time. If you do it in your head, man, I think for most people it's like 50-50. So lay it out. You know how to do this, just lay it out. And then let's do these two problems now. What is the magnitude of a force experienced by a positive 4 Coulomb charge? So positive 4 Coulomb charge that is located 2 meters. So that's 2 meters from a positive 8 Coulomb charge. So I'm going to draw my diagram. Remember to visualize. And I want to know what is the magnitude of the force experienced by the positive 4 Coulomb charge. So I want to know the size of that. I say, well, F is equal to KE Q, big Q, little q, over R squared. And yes, I don't want the signs. So I put these in absolute values. I don't want the signs. Forget about the signs. That gives you directionality. And then I turn around and say, well, this is KE. It's going to be 4 times 8 over 2 squared. So F is equal to, well, that looks to me like it's going to be 8 KE newtons. And it's common, certainly in my class, I don't require students to multiply out by KE. I want them to do as many questions as they can. So I say just write down KE. That's the magnitude. It's just a scalar. It's got no directionality to it. I could have drawn my diagram the other way and the directions would have been different. So it's appropriate that it has no directionality to it. But every now and then I want directionality. And so this is another example. So a 3 Coulomb point charge, positive, 3 positive, is located at, this is a long one. So this is going to be 2I plus 3J plus 4K meters. Well, that means from the origin. Yeah. And then a 12 Coulomb positive. Is it positive? Yes. Is located at 3I plus 5J plus 1K meters from the origin. Now I want to know, write an expression for the force experienced by the 3 Coulomb point charge. So I'm up at the top and I want to know the force experienced by this guy. And it's positive playing against positive, so that's going to be my force. It's important that you identify that direction. Well, let's write down an expression. We can say the vector force is equal to KE, big Q, little q, over R squared times R hat. If I try to put numbers in, I see that this is KE. Well, I don't worry about the sign, but I know the big one has 12 coulombs and the little one has 3 coulombs. And then I run into a problem because I don't know my separation. But I know that I can represent it by a vector between the two. And so I have a choice. Do I represent it by a vector going from the 3 towards the 12 or from the 12 towards the 3? And I'm going to represent it a bit perversely. I'm going to represent it like that. Going away. I just happen to pick it that way. And I say, well, that's R1. And let's call this one R2. And let's call this one R3. Okay. Because I've got to do some a bit of matrix, a bit of vector stuff here. Got to get an equation that links these 3 vectors. And if you look at the diagram, the equation is clear because you drew the diagram in a certain way. The process of addition is putting the tail of the second vector on the head of the first vector. So I have, whether I realized it or not, I have made a diagram where I took R1 and added it to R2. And that gave me a resultant. Resultant goes from the beginning of the beginning to the end of the end, which is R3. Because of the way I drew my diagram, that's what I have. Now I want to find R1. So I say, well, R1 is equal to R3 minus R2. Okay, so I need to do a matrix here, IJK. And let's write down R3. I know R3, it's down at the bottom. So it's 3I, 5J, and 1K. That's R3. And I've got to subtract from this R2. R2 I also know. Let's make it minus R2. So that's minus 2, minus 3, minus 4. Do you see what I did there? Rather than subtracting plus R2, I put down minus R2. I reverse the signs. Plus 2 went to minus 2, plus 3 went to minus 3, plus 4 went to minus 4. And now I can just add them, and I get 1, 2, minus 3. So what this is telling me is that R1 is equal to 1I plus 2J minus 3K meters. Okay. Now what that tells me is that the magnitude of R1, that's the R1 without a little arrow on top, is equal to the square root of 1 squared plus 2 squared plus, not minus, plus minus 3 squared. So R1 is equal to 1 plus 4 is 5 plus 9 is 14. So R1 is the square root of 14 meters long. Oh, so I can take this up here and I can say this is over the square root of 14 squared. So what did I just do? I looked at a vector diagram that I drew and I picked a direction for my displacement vector between the two charges. I used my vector skills to be able to calculate what that vector's IJK coordinates were, and I then used my knowledge about magnitudes of IJK vectors to figure out what the size, what the length of that vector was. I still have R squared though, so I need to do a bit more work. And I look at my diagram, and this is where people, I think, tend to, kind of get a bit confused. They know what they want, and they know this is in the same line, but can you see how it's in the wrong direction? So what I say is, oh, vector F is equal to 36ke over, well, it's going to be square root of 14 times another vector. And that vector, well, if I put down this original vector, this R1, that would be 1I plus 2j minus 3k. That's the correct line, but it's the opposite direction. Force is going up and to the left, my displacement vector that I chose to draw it going down and to the right. It's just the wrong direction. It's opposite. So I could put a negative sign in front of here. It's probably more memorable if I swap these signs. So let's do the opposite direction. So this would be not 1 but minus 1. This is not 2 but minus 2. And this is not 3 but plus 3. Not minus 3 but plus 3. Problem is it's too long. It's not a unit vector. It's got, well, it's square root of 14 meters long. Well, so what do I do now? Oh, I know. To get the unit vector, you divide a vector by its own magnitude. And that's what I just worked out. So this will be over square root of 14. So my expression for force is F is equal to 36 KE over 14 minus 1I minus 2J plus 3K over the square root of 14. Can put little unit vector hats on. And there's one more thing that's missing. Can you spot what it is? Of course it's units. I put all those letters down, but none of them were units. So I need to make sure I put my units down. Is that answer there? 36 over 14, it's one of the first two. The first one is nearly right, but it's the wrong direction. The second one is right. So it's going to be B. A lot going on in this question. When I do tests, this question pretty well comes up because it's a skill arithmetic is really important. You don't necessarily get a question where I give you the position of two charges from the origin. I could make it shorter by giving you two charges and their displacement vector, in which case I'm giving you R1, so you don't need to do this stuff in the bottom left hand corner. But either way, you have to be able to draw out this expression. I don't want my students to give me a final answer because I can look at this and see, well, I can see how they got the 36 and I can see where the 14 came from, and I can see how they got the direction for this vector, and I can see how they got the magnitude to be right. They scaled it into being a unit vector. If you leave it uncalculated, unmultiplied or divided, I can see what you're doing. If you multiply it out and you make a slip, I can't tell necessarily where you made the slip. So I say for my students, what is this expression? You know, write an expression for it, and that's what I mean. So watch out for it. If you're in my class, it's coming. There we have it.